This project focuses on MATLAB simulation modifications of code division multiple access systems in order to measure the performance increase obtained by implementing multi-user detection algorithms. CDMA is a wireless communication protocol that is used in 2G and 3G cellular systems. The system utilizes a spread spectrum technique that enables multiple users to communicate while using the same frequency at the same time. The system spreads the bandwidth across the entire spectrum equally. Utilizing CDMA systems greatly increases the number of users that each communication system can service. This image depicts the layout of a CDMA system. It is shown that multiple channels are stacked on top of each other and are operating at the same time over the same frequency. CDMA consists of two types of code, synchronous and asynchronous. Synchronous codes operate by modulating the transmitted signal so that it is orthogonal to the other signals in the channel. The nature of the dot product of orthogonal signals results in the elimination of interference between the signals of interest. Asynchronous codes operate using pseudo-random binary sequences. The codes generated in asynchronous CDMA systems appear to be random. However, they can be decoded by receivers that expect the code sequence of the transmitted signal. CDMA receivers use decorrelation to ignore signals that do not match the pseudo-random code of the transmitter. While CDMA systems help to increase the number of users in a communication system, the noise floor of the system is also increased. The noise floor is defined as the sum of all of the noise sources in a system. The system does not have an artificial limit on the number of users it can service. However, the performance of the system decreases as the noise floor increases. An important performance control aspect of CDMA is power control. The transmission power of users in the system must be modified based upon the distance between a base station and the user's device. If power control is not used, the noise floor can become significantly increased by a user dominating the signal at the base station. This can cause the base station to not receive weaker signals in the channel, which can cause service disruptions to users with weaker signals. This phenomenon is known as the near-far problem. A common method used to address both an increased noise floor and the near-far problem is through the implementation of multi-user detection algorithms. User signals are all considered to be beneficial to each other in CDMA systems that implement multi-user detection. Multi-user detection attempts to demodulate communication system users simultaneously when multiple access interference is present, which can help lead to increased efficiency in a larger number of users. Demodulation is achieved through the use of multiple matched filters, with each individual filter matching a user's pseudocode signal. There are multiple MUD algorithm types which each have their unique advantages and disadvantages. Linear multi-user detectors attempt to apply a linear transformation to a matched filter. This project focuses on two types of multi-user detectors, a decorrelation filter and a minimum mean square error filter. Decorrelating MUDs apply the inverse of the correlation matrix to achieve decorrelation with the matched filter. Minimum mean square error MUDs concentrate on minimizing the mean square error at the receiver. The effectiveness of communication channels can be reduced by many different types of effects. A common method used to quantify the effects of channel noise is to combine a communication signal with a noise model known as additive white Gaussian noise. Additive white Gaussian noise consists of a Gaussian distribution to spread a randomly generated noise signal over a channel. MATLAB features an additive white Gaussian noise function that can be used to easily simulate a common noise source. The Gaussian distribution of additive white Gaussian noise has the probability density function as shown. Another common type of channel hindrance is known as signal fading. As the transmitted signal propagates through a medium, the signal will experience fading due to free space loss, objects within the line of sight, weather, and other effects. A common method used to quantify signal fading is called Rayleigh fading. Rayleigh fading is based upon a statistical model and is used to quantify the randomness of signal fading as it passes through a medium. Channel coding attempts to mitigate the effects of both additive white Gaussian noise and Rayleigh fading. A Rayleigh distribution has a probability density function as shown below. There are many different modulation schemes, each with their own advantages and disadvantages. Modulation types produce varying bit errors, also known as BER. BER is a very important statistic when evaluating a modulation scheme. If the BER of a system is low, the probability of successfully receiving a correct data symbol will be high. Some systems attempt to resend transmissions at varying intervals to ensure a message is received. However, a low BER leads to a reduction in the need to retransmit messages since there is a higher probability of successful message reception. The power spectral density of a modulation type must be considered when evaluating whether or not the system will cause adjacent channel interference. An optimal modulation scheme has a high spectral efficiency with regards to adjacent channels. Power efficiency is critical, especially for battery-powered devices. Small envelope fluctuations are ideal after modulation to reduce the amount of unnecessary battery usage. Some of the modulation techniques explored in this project include binary phase shift keying, quadrature phase shift keying, and quadrature amplitude modulation. BPSK is a form of modulation that assigns a 1 or 0 to each received signal based upon a threshold setting. If the received signal's power level is above the threshold, BPSK assigns the message symbol to 1. Conversely, if the symbol is below the threshold, the message symbol will be assigned as a 0. The BPSK message scheme is described on this slide. QPSK modulation works by assigning 4 points around a constellation diagram to different message symbols. QPSK doubles the number of symbols detected over BPSK. This increased data rate can lead to a higher BER due to a large number of decision threshold areas. The extra threshold areas are achieved by observing the phase shift of the incoming message. The QPSK message constellation is shown here. QAM modulation expands upon the constellation diagram of QPSK. Depending upon the bit scheme chosen, QAM implements more symbols than both BPSK and QPSK. QAM also uses the phase shift of the incoming signal to determine the message's symbol. The message constellation for a 16 QAM modulation scheme is shown here. This project employs multiple MATLAB simulations to imitate CDMA systems. MUD algorithms are also implemented within the CDMA simulations. The difference in performance increase achieved by implementing multiple MUDs is quantified. Both additive white Gaussian noise and Rayleigh fading were implemented in MATLAB and used to compare the performance of the CDMA system to simulations without noise or fading. The main performance indicator used to compare the various MATLAB simulations involved plotting the bit error rate versus the signal-to-noise ratio. The equation for the BER performance of phase shift keying modulation types is shown here. The BER of QPSK is defined as the sum of two orthogonal BPSK symbols. When Rayleigh fading is added to the MATLAB simulation, the BER performance equation is modified as shown. The BER performance equation of a square MQAM modulated system is shown here below. A MathWorks MATLAB simulation of a BPSK CDMA system was modified to produce both a theoretical and a simulated BER curve for a CDMA system subjected to white Gaussian noise. The simulated system mimics the theoretical BER curve for a CDMA system. The theoretical additive white Gaussian noise channel was combined with a Rayleigh fading simulation to demonstrate the difference in BER achieved when the CDMA system is subjected to the two channel hindrance effects. The Rayleigh fading simulation also closely matched the theoretical BER curve. The CDMA system subjected to a Rayleigh fading channel requires a much larger signal-to-noise ratio in order to achieve the same bit error rate as a system only subjected to noise. The system in noise requires a signal-to-noise ratio of more than 5 dB to achieve a BER of less than 10 to the minus 2, while the system in a Rayleigh fading channel does not achieve the same BER until the signal-to-noise ratio is over 15 dB. The BER due to additive white Gaussian noise is an effect that can be much more easily overcome than Rayleigh fading. A comparison between different modulation schemes was conducted for CDMA systems subjected to both additive white Gaussian noise and Rayleigh fading. A CDMA system with QPSK modulation was simulated and compared to the BER performance achieved through the use of BPSK. The results of this simulation indicate that the BER of QPSK modulation, when subjected to noise, requires a higher signal-to-noise ratio to achieve the same BER as BPSK modulated systems. The same QPSK system was also subjected to Rayleigh fading. The results of the QPSK modulated CDMA system in a Rayleigh fading channel followed the same trend as the simulation in noise. The BER of QPSK systems is higher than BPSK modulated systems at the same signal-to-noise ratio. A CDMA system with 16 QAM modulation was implemented in MATLAB and subjected to both noise and Rayleigh fading. The BER curve indicates that both QPSK and 16 QAM modulation require a higher signal-to-noise ratio and subjected to noise in comparison to BPSK. The same 16 QAM system is also subjected to Rayleigh fading. The 16 QAM modulated CDMA system required a higher signal-to-noise ratio to achieve the same BER as either QPSK or BPSK. While these simulations indicate that BPSK is able to achieve a much lower BER for a specified signal-to-noise ratio, the increased message size of both QPSK and 16 QAM would need to be considered as a trade-off when designing a CDMA system. In order to compare the effectiveness of MUD algorithms, the MATLAB simulations used were modified to include a simple matched filter. The matched filter only detects single users and was implemented as a baseline measurement. The signal-to-noise ratio of the MUD algorithm simulations was significantly decreased in order to generate a higher BER for a large-valued comparison. The signal-to-noise ratio used was between negative 30 dB and negative 12 dB. First, 100,000 bits were generated and passed through the transmission channel. Unique CDMA codes were generated for each of the 10 users in the simulations. The multi-user detection algorithm simulations were each subjected to additive white Gaussian noise as a transmission hindrance. The BER curve of the matched filter is shown here. The performance of the 10-user matched filter simulation does not incorporate any MUD algorithms. The matched filter simulation should produce the worst-case scenario when compared to MUD-enabled simulations. A very high BER of between 36% and 48% was observed due to the very small signal-to-noise ratio simulated. Next, a decorrelation filter was modified into the simulation. A decorrelation filter is a linear MUD algorithm that attempts to apply the inverse of the correlation matrix to achieve decorrelation with the matched filter. The MATLAB simulation results obtained when utilizing a decorrelation filter in a CDMA system are shown. The decorrelation filter simulation did not produce a steady BER curve in the very low signal-to-noise ratio area observed. Conversely, the simulation did successfully produce a BER curve that had a lower BER range when compared to the matched filter without a multi-user detection algorithm. The BER range of the decorrelation filter was from 36% to 44.5%. The MMSE filter was modified into the MATLAB simulation. MMSE MUDs operate by minimizing the mean square error at the receiver in order to reduce the occurrence of message symbol errors. The MATLAB simulation results obtained through the use of an MMSE MUD algorithm are shown. The MMSE filtered simulation produced a BER curve that ranged from 33% to 43.5%. The larger the number of users, the more the filter is able to minimize the occurrence of incorrectly received symbols. MMSE operates on an a posteriori principle that uses past information to more correctly predict future results. In order to easily compare the matched filter, decorrelated filter, and MMSE filter against each other, the combination simulation was created. The results of the combination simulation are shown here. The decorrelation filter had an increase in BER across the signal-to-noise ratio range that averaged about 2.13% over the matched filter. The decrease in BER when progressing from the same baseline matched filter to the MMSE filter produced an average BER improvement of 4.40%. The MMSE filter had the best BER versus SNR chart with an average improvement of 2.27 over the decorrelated filter. There are many scholarly articles that explore the performance of CDMA systems. Most studies implement MUD algorithms as a method to improve the BER at a specific signal-to-noise ratio in comparison to systems without user detection. One project attempted to simplify MUDs within a CDMA system. The study simulated both a zero-forcing linear MUD and an MMSE linear MUD. The Viterbi decoder was also combined with the zero-forcing MUD. A Viterbi decoder operates through the use of maximum likelihood decoding algorithms. A baseline comparison without a MUD algorithm was simulated as a single user matched filter. The BER curve of the zero-forcing MUD system is shown here. The zero-forcing MUD resulted in an improvement in BER over the baseline matched filter. Additionally, the zero-forcing MUD with a Viterbi decoder achieved a significant improvement in BER over the standalone zero-forcing MUD. The MMSE linear MUD was simulated and compared to both the zero-forcing MUD and the baseline matched filter as shown here. The simulation indicates that the zero-forcing MUD has a higher BER than the baseline matched filter at very low signal-to-noise ratios. The study proposed that the zero-forcing MUD has a poor BER performance at low signal-to-noise ratios due to the fact that the algorithm operates based upon the principle of channel inversion. The MMSE MUD simulation outperformed both the baseline matched filter and the zero-forcing MUD by producing a lower BER across the signal-to-noise ratio range. It was observed that the MMSE MUD's performance increase was due to the fact that it accounts for additive white Gaussian noise, unlike the zero-forcing MUD. This project has demonstrated the BER performance differences achieved when simulating multiple features of a CDMA system. The implementation of MUD algorithms in CDMA systems greatly decreases the rate of errors received as the number of users is increased. This project has shown that while all MUD algorithms produce an improvement in BER over a standard matched filter, the MMSE filter was the best performing MUD tested in this project. The MMSE filter produced an average improvement of 4.40% over the matched filter and a 2.27 average improvement over the decorrelated filter at the SNR simulation range used.